So this is the talk about MariaDB and MySQL, about statistics that optimizer needs to optimize for queries, and when and how not to use indexes. Okay, so I work in MariaDB preparation as chief architect MariaDB, and I was working on MySQL code base for like 20 years, so I'm pretty familiar with it. But let's start the talk. So what statistics optimizer need? So when optimizer optimizes your query, it needs to know something about the data. And usually, well, traditionally it was done by optimizer was asking engine different questions, like, I don't know, how many rows does this table have, or how much would it cost to do the full table scan? And cost is in some arbitrary cost units, not in microseconds or CPU cycles or anything. Or for example, how much would it cost to read 1,000 values from the index number 3? And then optimizer would compare this cost with the cost of the full table scan and decide whether it's cheaper. Or how many distinct values are in the index? And then if the index has, say, 10 million rows and there are 1 million distinct values, then optimizer would assume that every value is present about 10 times in the index. Or optimizer could ask how many rows, how many index values lie in the range between, say, 10,000 and 11,000. And then it would ask the cost to read them, and then it would compare with the full table scan, and so on. That works reasonably well, but there are some issues with that. And one of the problems is instability. Not all engines has these values all the time ready. They calculate them on the fly, and MariaDB, for example, is doing it using random index dives. And because they are random, they supposedly don't have any bias. On the other hand, because they are random, they do not give repeatable results. And those are the tests I've done on DBT3 benchmarks on a query from DBT3 number Q8. There are 8 InDB tables involved in this query. And just by repeating it many times, I've seen 4 different execution plans, and with a query execution time ranging from 7 minutes to 1.2 hours. And for Q7, I've seen 7 different plans. The fastest one was executing in 12 minutes, and the longest one, I just waited for a few hours and killed the query because, yeah, I got impatient. So it's not what you would prefer to have. Some might ask, what about MariaDB persistent statistics? And it does solve the instability problem in a way that MariaDB is still doing those random dives, and then it remembers the result in an internal table, and next time it will just show you the same result. So there's no instability, you always get the same result and the same execution plan. But because it still started from the random dives, if you're lucky, you'll get always the same execution plan, and the query will always execute in 12 minutes. If you're unlucky, you'll get always the same plan, and it'll always be many hours and timeout. If you don't even know how many plans are there, so if you might just think the query is slow if it always times out after many hours, but it may be just that you got bad random dives. Another problem is that all engines, they do report statistics in arbitrary cost units, but they are different cost units for different engines, and engines lie about what data are in the table. This is the example. I have a table with 3 integer columns, and I populated every column with a random number between 10 and 100,000, and repeated it 400,000 times. And now I do select count distinct, which is honest, exact SQL calculation to get the number of distinct values. And what do you think what number I'll get here? Anybody could guess? Who's not looking in his own laptop? Okay, it was 400,000 rows, and numbers are between 0 and 100,000, so it should be about 100,000 distinct values, and this is exactly what I've got. But this query, it takes a lot of time to calculate, so usually optimizer relies on some imprecise estimations done by the engine. So the engine is MyISM here, and here I asked the engine for the estimation how many distinct values are in the index. And MyISM estimated, which it's not exact number, but it's within 1%, which is good enough for the optimizer planning point of view. Now I change the table to MariaDB, and we'll not waste time trying to guess. MariaDB reports 200,000 distinct values, And if you remember that the table contains integers between 0 and 100,000, there cannot possibly be 200,000 distinct values in there. But what does it mean for the optimizer? So there are optimizer knows that there are 400,000 rows in the table, and there are 100 distinct values. It means that optimizer would expect every single value to be present in the table 4 times. If you look for the specific value, optimizer would expect to find 4 rows. But in a DB light, there are twice as many distinct values as there actually are, so optimizer would think there are only 2 rows to be found. So optimizer will be more likely to prefer an index in a DB case because in a DB lies about statistics. And why InnoDB is doing that? Well, like 15 to 20 years ago, the original InnoDB author back then, Heikki Tuuri, he just noticed that for some query InnoDB doesn't use the index, and he would like MySQL to use the index. So he just added ×2 and make the index twice as more attractive to the optimizer, and he was happy with that. And since then, because there are many years past, optimizer just kind of adapted, and it's probably embedded in many parts of the optimizer, the assumption that InnoDB is doing that. And as far as I know, they've removed this ×2 in MySQL 8. So the other problem, of course, that if you need all these statistics, you need an index. In index, you need to pay the price for an index. Index, they take space, they takes time to be maintained, and often if you just need statistics, then index, it's just too much price to pay, it's too expensive. And a solution, so from now on I'll be talking about MariaDB for a while, and then later I'll describe the differences with MySQL and new MariaDB versions. So this is the solution that was implemented in MariaDB called engine-independent table statistics. And it provides stable, precise, detailed, and comparable statistics. So it's stable because statistics is calculated once and then stored in persistent tables. It's not calculated every time using some random dives. It's precise because MariaDB analyzes all the data, not just a very, very small percentage of the data. So it gets a very good representation of what the data is, and statistics is actually close to actual data. It's detailed because this engine-independent statistic remembers a lot more information than just cardinality, than just one number. So it allows optimizers to know more about the data and create better execution plans. And it's calculated by the server, not by the engine, so it's calculated identical for all engines. So cost estimations are identical, and they're comparable, so optimizer can calculate the cost for one table in one engine and for another table in different engine, and then compare them and decide in what order it's better to execute the query, for example, a join. Now, I'm not going to recite the manual, so this is I'm just giving you a few pointers, a few keywords. If you're interested, you either download my talk later or just make a picture of the slide, and these are the words you can later look up in the manual. So very briefly, it is implemented by having new tables in the MySQL schema where all the information, all the statistics is stored. There's a new system variable called useStatTables that tells the optimizer when to use information, these engine-independent statistics. It could be never used or preferable and so on. And there's optimized use condition selectivity, which I'll be talking about for the rest of my talk, which tells the optimizer which exactly parts of the engine-independent statistics optimizer is allowed to use. And there are optional clauses in the analyze table where you can specify what parts of the table should be for what parts of the table the statistics should be calculated. It could be done for all table or for only some indexes or for only some columns. But enough this theory, now let's get to the examples. And for the examples, I use the employees database, which can be downloaded from the Giuseppe's GitHub, and Giuseppe was the guy who was giving talk just before. It's not a very big data set, but it's not exactly small either. It's 167 megabytes of data, and the employees table has 300,000 records, and salary table has like 2.8 million records. So let's load it. You need to download it from the Giuseppe GitHub, then you do source employees.sql, which creates all the table and performs all the load data to load all the data. And then I enable engine-independent table statistics by setting useStatTables preferably. And then I analyze all the table to collect the statistics. There's no need to specify any optional clauses for the analyze here, because if statistics is enabled preferably, then Analyze will automatically collect all the engine-independent statistics. So you don't need to modify your application and rewrite all the Analyze table statements. You just need to enable engine-independent statistics once, and then it will automatically work for the all of your application. And you can see that it's not a very big data set because this one took only less than 30 seconds. So how does this one help to optimize your queries? First, I said optimize use condition selectivity 1, which tells optimizer not to use any engine-independent statistics. Basically, it only uses the data that were available before engine-independent statistics was introduced. And I want to find all the managers from all departments in this example employees database. So I join departments with employees, with manager, with titles, where title equals manager. And for the purpose of this example, it's important to remember that title column is not indexed. So then MariaDB does something with the data and returns the result set in 15 seconds. Now I enable optimize use condition selectivity 3, which allows optimizer to use per column statistics for non-indexed columns. And the same query is executed under a second. This is 16 times improvement. It's not 16%, it's not 1.6 times, it's 16 times improvement. And so it's pretty remarkable to me. And let's see why does this happen. This is a result of explain extended for the first query when the optimizer cannot use per column statistics. It is explain extended, so there's column filtered, which tells what percentage of the table optimizer thinks will pass the where clause. And because there's no data available for non-indexed columns, optimizer doesn't know, so he just says 100% everything might pass the where clause. But if we allow optimizer to use per column statistics for not indexed columns, then optimizer knows the cardinality for non-indexed columns and minimal and maximal value for non-indexed columns. And optimizer can figure out that not all employees are in fact managers, and only about 14% of the titles will match the where clause. And in this case, optimizer decides to join tables in different order and start from full table scan of the titles table, and this gives 16 times improvement. Now, before talking about histograms, I want to explain what the equi-height histogram is. This is not an equi-height histogram. It's a usual histogram that you see everywhere. It's equi-width histograms. The red line just shows some imaginary data distribution, and this is histogram for this data distribution under the red line. I've drawn it with 5 bars, 5 buckets. They all have the same width. That's why it's called equi-width, and the height of the bar is proportional to the area under the curve. And this is the equi-height histogram, where all the bars have the same height, but different width. There are also 5 of them, but in this case, the area under the curve must be always the same. And why would we want to do this strange thing instead of normal histograms? Because all we remember for every column is those 5 numbers. Well, more than 5, but still fixed number of bars to describe a histogram. And then later, optimizer needs to use this data to kind of restore the original data distribution, to understand the original data distribution. And if optimizer would try to restore the original distribution based on the equi-width histogram, this is what it would get. You see there's a huge error in the most interesting part of the curve where the values are high. And if you try to restore the curve from the equi-height histogram, the interesting part of the curve is described much more precisely, the error is much smaller. Basically, equi-height histogram allows you to describe the data distribution much more precisely with a smaller number of values. This is what MariaDB is using for histograms. Now let's see how histograms are helping to optimize the queries. And for this one, we need an example of some data with non-uniform distribution. Let's look at the salary values from the employees database, and we calculate the midpoint of mid salary. That's exactly in the middle between minimal and maximal salary. That's the first query. It's about 100,000. And now let's select all the employees and their titles from the salary table, where the salary was above the midpoint, above the 100,000. Again, in some time after turning some data, MariaDB returns a result in 18 seconds, 19 seconds. But if we enable the use of histograms by setting optimize use condition selectivity equals 4, we'll get the same result 3 times faster. Again, why is this happening? Because if you don't use histograms, then all the data that optimizer knows about the table is it knows the minimal value for the salary, it knows the maximal value for the salary. And because we are searching for everything which is above the midpoint, optimizer can figure out, okay, so this is midpoint. So about half of the data should be above midpoint, about half of the data should be below midpoint. That would optimizer thinks, and indeed if you see the filtered column is about 50%. Let's optimize the thing that half of the rows will pass the where clause. But that at least half of the rows would have passed the where clause if the salaries would be distributed uniformly. But in this employees database, just like in the real world, salaries are distributed very non-uniformly. And if we enable histograms, optimizer can see that indeed only less than 5% of salaries lie above the midpoint. In this case, optimizer again joins tables in different order and this gives a 3 times speed up. The next interesting feature that was implemented is sampling. So this is a query which could be realistically used by, I don't know, HR department by analyzing whether there's salaries are distributed fairly or there's some people are getting low salaries based on, I don't know, sex or origin or whatever. So this query, it takes the average salary per department for all the people whose last name ends with "of," which supposedly could mean people with Slavic origin. As you know, those kind of queries, you cannot optimize it. You cannot optimize it from the index. You cannot get any reasonable histogram for that. You cannot get any reasonable statistics for that. So optimizer doesn't know anything about this. And it finds 5 rows because it's grouped by department in 5 seconds. And if you enable sampling, you get the same result 12 times faster. Yes. So how does sampling work? Because there's no other way for optimizer to get any reasonable information about the data. It reads few rows from the table and applies this like condition, and then it extrapolates the result to the rest of the table. And indeed, without sampling, you can see that filtered column is 100% because there's no histograms, no indexes, nothing that could help optimizer to know anything about the data. And with sampling, optimizer can realize that indeed there are very few rows that matches that where clause. And it optimizes joins tables in different order, and this is 12 times speed up. Everything that I was talking about now, it was implemented in MariaDB 10.0, which went GA in 2014, so it's quite stable. Well, in fact, 10.0 is already reached its end of life, so don't use that, use at least 10.1. And in this MariaDB 10.0, engine independent statistic remembers the number of rows per table and the cardinality per index. And for every column, it remembers number of distinct values, minimal and maximal value, amount of nulls, average value length for strings, and this equi-height histogram. And sampling also works. Last year, MySQL 8.0 went GA. They implemented a conceptually similar feature. It's called differently. It's called optimized statistic in MySQL, and they remember amount of nulls per column. But they have two different kinds of histograms. They have equi-height histograms and singleton histograms. And singleton work much better than equi-height if you have data with very few distinct values. Like if you have a sex column or a column with yes/no values. This case where singleton histograms work and equi-height basically don't. Also, if you try to collect a histogram for a really huge table, then MySQL starts keeping values to keep all the data in memory, and it gives significant speed up as compared to how MariaDB 10.0 collects histograms on the huge tables. And in a few months, MariaDB 10.4 will become GA, where this engine dependency is enabled by default, which is basically the main reason why I'm giving this talk. So if you start upgrading, you should know this enabled by default. You don't need to do anything anymore. Everything will just automatically and magically will be faster. And MariaDB 10.4 also collects histogram by sampling, by skipping values, so that analyzed table will be fast and in MariaDB before 10.4, analyze for engine-specific statistics was slow. This was the reason why it wasn't enabled by default. And this feature was mostly implemented as a Google Summer of Code project last year. That's all. Thank you. Have any questions? Yes?
Normally when I run a query twice, so normally some data gets into the pool buffer or
Yeah.
already on the file system cache or something.
Yeah.
Can you make these tests? So what is the test on two different systems or how
Yeah.
what is caching and relate what you're doing?
Are you talking about this one? Yeah, so the question is about how I compared the results and execution times for the same query. It was the same system, and I would just repeat it many times. I repeated explain many times. I repeated just select many times in different order. And I was collecting how many different selects, how many different explains output I would see. And caching does not affect the explain output. And yeah, execution time as well. I think after the cache was warmed up, so this shouldn't be taken into account. After the result, I was only collecting the results that were stable. Yes?
Get the statistic a little bit like MariaDB that's what inside the branch. Or is it still based on analyze table?
I'm sorry, I didn't get that.
Is there a plan to collect the statistic on the fly and not?
So the question is there any plans to collect statistics on the fly? We are thinking about that, but it will not be in MariaDB 10.4.